This presentation is for the Trem-Mellow guitar effect pedal, which was designed and built to satisfy requirements for the course EE325. The project objectives were to design and implement an analog or mixed signal system, build a printed circuit board, then test and validate the operation of the circuit. Tremolo, as an effect, is used to modulate the volume of a guitar or other instrument without a change in performance from the musician. This makes it an ideal effect to automate with an analog circuit. The first tremolo effect was achieved through an electromechanical system in which a motor drove a spindle to shake a vial of electrolytic fluid. The time-varying flow of electrolytic fluid is an excellent example of a physical system which can be appropriately modeled by an analog electric circuit. The goal of the circuit is to modify the amplitude, the envelope of the carrier wave, in this case the original guitar performance, with a time-varying control voltage. The circuit will consist of the following: an oscillator, an integrator to shape the output waveform from the oscillator, a tunable bandpass filter with a constant Q where the center frequency will be controlled by the output of the integrator, a MOSFET preamp to apply gain to the incoming guitar signal, and an amplifier output stage to make up any gain lost throughout the circuit. The cornerstone of the time-varying control voltage begins with an EE325 timer IC configured as an astable multi-vibrator oscillator. The 555 output frequency should be less than 20 Hz in order for the effect to be perceived as a rhythmic pulsing rather than a distinct, audible tone. A 100 kΩ potentiometer will allow the musician to control the speed of the tremolo effect. In our circuit, the frequency of the 555 has been limited from 0.65 Hz to just under 7 Hz. The duty cycle of this implementation of the 555 timer is larger, fixed to approximately 50%. The intent of Trem-Mellow, as implied in the name, is to provide a subtle tremolo effect. The square wave output from the 555 timer is passed into an integrator. The integrator corner frequency of 0.398 Hz ensures that even the lowest selected frequency is transformed into a triangle wave with a modest slope. The integrator operated well at the low end of the clock frequency. The reduction in gain as the clock frequency increased was not considered prior to implementation. The perceived depth of the effect is controlled by the peak-to-peak voltage swing at the output of the integrator. Further revisions would include a frequency compensating amplifier to apply makeup gain before the LED output. An equal component multiple feedback bandpass filter completes the heart of the circuit. Since the intent is to modify the volume of the signal and not necessarily the frequencies that compose the signal, choosing a wide band response with AQ of 1 is sufficient. Further, since the LM386 audio amplifier output stage will make up for any lost gain, it is not necessary for the filter to do anything other than attenuate. Through these design choices, we are able to select equal components for the filter. The choice of components was based on frequencies often perceptible and pleasing to humans. Consideration was also given to the frequency range, 80 Hz to 1.31 kHz, that make up the fundamental electric guitar tone. To confirm that the design would audibly behave as desired, a 15-second guitar audio wave was used as a voltage source. Here is the unprocessed 15-second audio clip immediately followed by the LT Spice processed audio. The control voltage as output by the integrator and the frequency of the filter are linked by two LEDs fed into light-dependent resistors. As measured in darkness, the resistance of the LDRs can be modeled as nearly an open circuit, several megohms. At full intensity, the resistance is negligible and the frequency is selected by the 47 ohm resistor. The result is a frequency sweep of center frequencies from 50 Hz to 70 kHz. An FFT of the frequency spectrum of a 250 Hz square wave test tone shows that the 3.2 Hz fixed control voltage does not meaningfully impart any errant sound on the carrier wave. Due to the 50 Hz to 70 kHz center frequency sweep, the envelope applied to the carrier wave is not linear. A restriction in time-varying resistance, and consequent restriction in center frequency sweep would result in the envelope being applied more evenly over the range of the tones the guitar is able to produce. The amplification of the signal takes place at the input and output. First, the input signal is amplified by a MOSFET with drain-to-gate biasing and with variable transconductance gain as controlled by a potentiometer at the source. The drain-to-gate feedback biasing ensures that the MOSFET is always saturated. The potentiometer allows a variable gain from just under 1 to 10. This is to ensure the input signal has an appropriate amplitude going into the MFB filter. The output of the MFB bandpass filter is fed into an LM386 audio amplifier. The open-loop gain of the LM386 is 200 and unnecessary for our application. By connecting a 10 nanofarad capacitor between pins 1 and 8 of the amplifier, we achieve an average gain of 20 across the entire guitar tone range. Selection of the LM386 was based on ubiquity of components, the wide range of supply voltages that the amplifier can operate under, and the ability to supply an output power of 700 mW minimum to an output load of 32 ohms. A Hammond 1590 enclosure was used to house the circuit board. The aluminum enclosure provides physical protection to the circuit due to the strength of material and corrosion resistance. A 3-pole double-through switch was used in order to provide a true bypass for the signal if the effect is not desired. Shorting of the signal path or power from the printed circuit board coming in contact with the aluminum was mitigated by the use of Kapton tape on the back side of the board. The layout of the printed circuit board was dominated by 3 constraints: the size of through-hole discrete components, the selection of only a 2-layer board, and by the 2.2-inch width of the enclosure in which it is mounted. The printed circuit board would ultimately prove to be the greatest foil to the design. Prior to routing components and ordering the circuit board, a physical mock-up of the Tremolo effect was breadboarded. The behavior of the circuit was exceptional despite the inherent parasitic capacitance and inductance that exist in prototypes. Despite fully assembling one pedal, the design team was unable to have the end product function as an acceptable tremolo. Test points were included on the schematic, and through troubleshooting the circuit board it was discovered that the signal was lost at the output of the filter. Soldering the components without creating a short caused the greatest amount of difficulty. Since the board was so narrow and the amount of traces was high, it raised the skill required in assembling the pedal. The printed circuit board and Hammond enclosure were the 2 most expensive items in our project. Failure of a discrete, soldered component is not physically easy to replace but is financially inconsequential. Choosing an enclosure with greater width and thereby a wider circuit board would have permitted for larger gaps between the traces. An alternative to the 555 timer would be an 8-bit microcontroller such as the EE325. With the pulse width modulation outputs of the microcontroller, the programmer could allow the end user to create a clock signal of arbitrary duty cycle. Such a clock signal could be fed into an integrator with user-controlled corner frequency to allow waveform selection from square wave, to triangle, to sine. Further, if a larger enclosure is used, An additional depth parameter controlling waveform amplifier gain would allow the user to select from a subtle to aggressive modulation. This concludes the Trem-Mellow guitar pedal project. Despite being able to synthesize linear, second-order circuits from design constraints, we still failed in properly measuring physical dimensions of our enclosure. Oh well. I suppose that is why we are not enrolled in mechanical engineering. Please allow this tune demonstrating our pedal to soothe your fears about releasing us into the wild to be engineers.